Hi, my name is Michael Farrell. I am a senior in mechanical engineering, and this is my second year on the AUVSI team. This year, I am the 2017 BYU UAV Team captain, and on the flight line, I will be the operations supervisor. Let's meet the team.
Hi, I'm Jeff Bergen. This is my second year on the team. I'm a senior, graduating this year. I was assistant team lead this year, worked on the autopilot, and really focused on the interop towards the end of the year, and on the flight line I will be working on the interop.
My name is Jesse Wynn. I'm a graduate student here at Brigham Young University. I've been on the design team for 2 years now. My role has been as the imaging sub-team leader, and my role at the competition will be the safety pilot.
I'm Anthony Gillespie, a senior in computer engineering. This is my first year with the team. I'm helping with the autopilot team, and at the competition I'll be a ground station operator.
Hi, I'm Jordan Berryhill. I'm a junior in mechanical engineering here at BYU. This is my first year with the UAV team, and I was the airframe and payload team lead. At the competition, I will be the communication equipment operator.
Hi, my name is Jaron. I'm a junior at BYU. I'm studying mechanical engineering. I've been on the team for about 2 years, mostly on the image analyzing team. At the competition, I'll be the image data specialist.
I'm Andrew Torgerson. I'm a junior in the mechanical engineering program here at BYU. This is my first year with the AUVSI team. I'm currently on the autopilot team, and in the competition I will be operating the ground station.
My name is Peter Schlady. I'm a senior, and this is my first year on the BYU team. I will be an imaging analyst at the flight line.
My name is Wesley Berrigan. I go to Brigham Young University. I'm on the BYU AUVSI team for 1 year now, and I am part of the imaging subsystem, and at the competition I'll be the image analyzer.
My name is Steve Rogers. I am a senior studying electrical engineering. This is my first year on the BYU UAV team, and I am the autopilot team lead, and I will be the flight director at the flight line.
This is our team's aircraft. It is the My Twin Dream EPO aircraft from Ready Made RC. It features twin motors that are powered by a 10,000 milliamp hour 4-cell lithium polymer battery. For RC communications, we have a Taranis QX7 radio system and the accompanying receiver. This communication happens on a spread spectrum 2.4 gigahertz link. For the data link between the onboard computer and the ground station, we have a PicoStation Ubiquiti 2.4 gigahertz link. The instruments on the aircraft, the external instruments include a Venus GPS module and a PX4 airspeed sensor. On the interior of the plane, we have an in-house built custom autopilot that features embedded firmware running on a small microprocessor known as ROS-Flight, and the autopilot is realized through the onboard computer, which runs the ROS plane autopilot software. Our team's primary vision sensor is the Sony FCV EV7500 block camera. It features a high-speed shutter, a 30x optical zoom, and internal image stabilization. The heart of our autopilot is a Flip 32 flight controller that has custom firmware called ROS-Flight running on board. This board allows us to get measurements such as IMU and barometer, and it also feeds outputs from the autopilot to the control surfaces of the aircraft. The second part of our team's autopilot is the onboard computer. The computer itself is a Gigabyte Bricks i5 computer running Ubuntu 16.04. The control loops of the autopilot are computed on the onboard computer, and commands are passed over a USB link to the ROS-Flight Flip 32 board. Our aircraft features a single-axis brushless gimbal that gimbals our primary camera to point out the side of the aircraft, and also directly out the bottom of the aircraft. In this configuration, it makes it possible to precisely geolocate targets while the aircraft flies a loiter or orbit pattern around the target location.
During the mission demonstration, we plan to attempt the following tests: autonomous flight, including waypoint capture, autonomous takeoff, and autonomous landing; static obstacle avoidance, and both manual and autonomous object detection, classification, and localization. We will not attempt moving obstacle avoidance, nor will we attempt the air delivery task. We are very confident in our ability to successfully complete the autonomous flight task, with capturing waypoints accurately, as well as autonomously taking off and landing the UAV. During flight, we are confident that we will avoid all static obstacles. We are also confident in our ability to manually detect, classify, and localize the ground objects. However, we expect only to receive partial credit for the autonomous detection, classification, and localization of these objects.
We wanted our UAV design to be as efficient as possible. As part of developmental testing, we evaluated the performance of different motor and propeller combinations to maximize our thrust-to-power ratio. These tests were performed with a thrust stand from RC Benchmark. We tested numerous motor and propeller combinations and compiled data for each individual one. Once all of the individual test results were in, we compared and plotted the results as found in our technical design paper. Finally, we selected the combination with the best thrust-to-power ratio that was compatible with our airframe.
So because we decided to use an autopilot system that was developed here in a research lab, we figured it would be best practice to first test out the autopilot in a simulation system, as well as run development on that simulation system. So the fact that our autopilot code and simulations run through the ROS framework allowed us to use our ground station GUI in tandem with the simulator, allowing for ground station development without needing to get a plane up in the air. Similar development took place with the simulator for obstacle avoidance, path planning algorithms, autonomous landing, and achieving increased waypoint accuracy. We were even able to do some preemptory tuning of our aircraft within the simulator. This was made possible by inputting aerodynamic coefficients which we were able to find online for the Twin Dream airframe.
Developmental testing has occurred over the past few months on the ROS Flight, ROS Plane autopilot system. Testing of the autopilot began on a test airframe known as the Bixler that we have conducted over 25 autonomous flights on. During these tests on our test airframe, we have tested new path planning algorithms as well as our waypoint capture accuracy. After we were confident in the autonomous flight capability of our autopilot on the test airframe, we ported it over to our competition airframe. We have now conducted 5 autonomous flights on our competition airframe. During these autonomous flights, we have spent an average of half of the flight time in manual mode and half of the flight time in autonomous mode. As we continue testing on our competition airframe, we plan to extend the time in autonomous mode to 100% of flight time. Tuning of the aircraft occurred in simulation and then in real autonomous flight. We first tuned the test airframe in both simulation and flight before tuning the competition airframe. The process of tuning the airframe included commanding different altitudes, airspeeds, and headings, and observing the aircraft's response. Based on the aircraft's response, we tuned the control gains in order to produce a well-tuned aircraft autopilot system.
Before flying waypoints in real flight, we tested flying waypoints in our simulation. We have a high-fidelity aerodynamic model of our aircraft, the My Twin Dream, in simulation, which we've been flying. We have tested numerous missions and over 100 waypoints in simulation and have achieved a waypoint accuracy of 95 to 99% while flying straight-line paths and 80 to 90% while flying Dubin's paths. The waypoints were achieved within 0 to 1 meters with straight-line paths and 0 to 5 meters using Dubin's paths. In real flight, we've attempted 30 waypoints on the Bixler airframe, which is our test airframe, and have achieved 30 of the 30 waypoints with a 0 to 40 meter accuracy. 50% of the achieved waypoints were within 10 to 15 meters.
One of our main concerns was our ability to hit waypoints accurately. In order to do this, we chose to use Dubin's paths, which are a type of flight that allows the plane to fly straight paths between points and then approach on circular paths to have a specified orientation at each point. However, there are potentially obstacles between waypoints, and so we implemented an RRT algorithm to randomly plan paths to avoid those obstacles. When a certain number of safe paths has been planned, which can be many because the algorithm runs quickly. The shortest one is selected, and the UAV flies around whatever obstacles. We've tested in simulation so far, and so far only on static obstacles. We've run 10 flight tests in simulation to avoid either 1 or 2 obstacles. We have been successful at avoiding 14 out of 15 obstacles.
For the imaging system and image performance, we are using a high definition Sony camera that takes pictures from the air on the side of the plane as it loiters around a desired area. Some of the tests that we've done in order to achieve accurate and clear images, we were taking images from the plane at approximately 150 feet in altitude, and we're able to 100% of the time classify those images. We also were able to do the same test but on the ground from 300 feet away and be able to accurately detect images and see them clearly.
For our image classification software, we chose to do 2 neural networks. The first was a spatial transform network, and the second was just a general classification deep convolution network. For about 1,400 training iterations, we have successfully identified shape color 100%, letter color 80%, shape 90% about, and then letter over 30%. But this is just preliminary results, and we have seen results over 75% for each category if we do more training iterations. And so this data is showing just a simple classification of these cropped images. So this shape is cropped, it's a square and S, and it classifies this image. But we are currently working on a neural network called a spatial transformer network, which takes a whole image like this and learns the transformation to crop out this image and then create an image like this, which will then get spit into the results here.
Our UAV has 2 cameras on it. The first is out the front and has a wide-angle lens for flying through the target area to find the locations of the objects. As it flies through, someone on the ground clicks on the image, and the clicks on each target are averaged to find a rough location. This image is sent over an RF antenna instead of through our digital communications, which frees up bandwidth for other things that the plane is doing. This image transmits right now at a 1076 by 576 resolution, and once the plane is finished flying through the target area, it flies loiters around each target. From those loiters, we look at the targets through a camera on the side, and that lets us save the images, which can be run through a learning algorithm later on.
Full mission testing has been underway according to the outline detailed in our technical design paper. In a full mission test last week, we crashed our competition airframe and since have been working around the clock to build and fly our backup airframe. During these competition tests, we have successfully been running an instance of the judges interop server and have successfully been uploading both telemetry data and object detection, classification, and localization data. For the full competition test, we have been flying the airframe remote controlled, so we have scored very well on all attempted tasks besides the autonomous flight and static obstacle avoidance. According to our schedule, we plan to attempt full mission tasks autonomously this week. These full mission tests show that we should succeed in the object detection, classification, and localization, as well as be able to supply telemetry data to the judges server at the appropriate rates. We have conducted several full mission tests of autonomous flight on our test airframe. However, we are yet to conduct a full mission test autonomously on our competition airframe. We plan to conduct this full mission test autonomously this week according to our schedule.